Hello everyone. So, this is the third lecture of week 4. So, recall that we have been learning about gradient descent algorithm, and yeah, so in the previous class we also learnt a new algorithm called coordinate descent algorithm. Coordinate descent algorithm is just I mean it follows the same steps as in gradient descent algorithm, just that instead of choosing dk as minus gk, we choose the negatives of the coordinates. Okay. And we saw that it works when f of x is of the form half x transpose hx, where h is a diagonal positive definite matrix. Okay. And we also saw that when it is not a diagonal matrix, we gave an example where the algorithm does not work. Okay. So, fine, if you recall that counter example, this it is f of x1 equal to x1 squared plus x1 x2 plus x2 squared, and h is actually 2 1 1 2. We saw that at the end of 2 steps we got something else and not 0 comma 0. So, is there a way to correct this? So, can we choose d0 and d1 intelligently in such a way that yeah, you get to 0 comma 0 in 2 steps. Okay. So, let me make an attempt and check if it works. Okay. So, let us say f of so the same example f of x1 x2 is half x transpose 2 1 1 2 x, and x0 let us say is 4 comma minus 5. So, I am choosing 4 comma minus 5 because I mean it is a slightly harder example. If it is 1 comma 1, the I mean the one that I am going to work out will give you an answer very easily. So, I am choosing a slightly harder example 4 comma minus 5. Okay. So, what am I going to do? I am going to choose d0 as minus 1 and d1 as 1 minus 1. Okay. So, let us see if these d0 and d1 actually gives me the solution in 2 steps. Okay. Let us work out the problem. So, you have x1 equal to x naught plus alpha naught d naught. So, it is 4 minus 5 plus, so alpha naught is minus g0 transpose d0 by okay. So, instead of writing all that, I will figure out what g0 is. So, g0 is 2 1 1 2 4 minus 5, which is 3 and minus 3. I suppose I am right, 4 sorry minus 6, 3 and minus 6. Okay. And yeah, so d0 transpose h d0 is just 2. So, yeah, so we have so and this has to be multiplied with or had dot product with minus 1 minus 1. So, you have 3 here, 3 by 2 minus 1 minus 1. So, you have 4 plus 3 by 2 is let us see 4 plus 3 by 2 is 5.5. So, I will just write it as 5.5 or 11 by 2, it is okay, and minus 5 plus 3 by 2 is yeah. So, it is minus 5 plus 3 by 2 is minus 3.5. Okay. So, let me check if I am doing this right at this point. So, yeah. So, this is G 0 which is 3 and 4 minus 10 is minus 6. Okay. So, you have G 0 transpose D 0 is minus 3 plus 6 which is 3. Okay. So, that is fine, and similarly D 0 transpose H D 0 is just the oh okay. So, this is different, I am sorry, it is going to be 2 plus 1 plus 1 plus 2. So, that is 6, yeah, I am sorry. So, this should be 6, and so this actually becomes, so this is half basically. So, 4 plus half is 4.5 and minus 5 plus half is minus 4.5. Okay. So, fine. So, that is x 1, x 1 is 4.5 minus 4.5. Now, let us find x 2 is x 1 plus alpha 1 d 1 which is 4.5 4.5. Okay. Now, again I have to do this. So, G 1 is 2 1 1 2 into 4.5 4.5 which is sorry minus 4.5. So, this is 9 minus 4.5 is 4.5 and this is 4.5 minus 9 is minus 4.5. So, G 1 transpose D 1 is so this is 4.5 plus 4.5 which is 9 and D 1 transpose H D 1 is 4 minus 2 is 2. Okay. So, it is 9 by 2, 1 minus 1. So, 4.5 minus 4.5 is 0 and sorry this is minus 4 minus 4.5 minus 4.5 is 0 again. Okay. So, great, I got the answer in 2 steps as I wanted to have it, right. So, and if you ask what change I did, instead of choosing the coordinates, the negatives of the coordinates, I chose a slightly different d 0 and d 1. So, if you see it is one is minus 1 comma minus 1 and the other is 1 comma minus 1. Okay. So, yeah, the issue of course as you can see is in the choice of right direction, is not it. So, I chose the steepest descent, that is the negative of the gradient always, and I mean I had a problem with lambda 1 by lambda n. I chose the negatives of the coordinates and I had a problem when the Hessian was not a diagonal matrix, right. So, but when I had a different Hessian, I just chose some different d 0, d 1 and so on, and I was able to converge in n steps, right. So, now the question is how do you know what d 1 d 2 or d 0 d 1 dot 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 d n minus 1 to be chosen, right. So, I mean let me even put this question a little more clearly. So, given that the Hessian is 2 1 1 2, okay, how do I come up with this d 0 and d 1 as d 0 is minus 1 and d 1 is 1 minus 1, right. So, the answer is very simple, choose the eigenvectors of the particular matrix. Okay. So, yeah, I mean you must have known matrix theory as much as to figure out what are eigenvalues and eigenvectors, right. So, given a matrix, blindly choose the eigenvectors of the matrix and you will actually converge to the right answer in n steps. Okay. So, and if you want I mean some illustrations of the statement that I just gave, please note that the eigenvectors of a diagonal matrix is just 1 0 0 0 0 1 0 0 0 0 1 0 0 0 dot 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 all zeros and 1, right. So, and that is exactly what we chose in coordinate descent method, and it worked when H was a diagonal matrix, right. When H is not a diagonal matrix, these are not the eigenvalues, and thus it did not work. Okay. And what are the eigenvalues of this matrix 2 1 1 2? Very simple, it is 1 1 and 1 minus 1. Why is that? So, yeah, you can, I mean you can check this, given that I have given the values, right. Eigenvectors of 2 1 1 2 is, I claim, are 1 1 and 1 minus 1. Why is that? So, just do a product of this matrix with 1 1, you get 3 into 1 comma 1. So, whenever you have A x is equal to lambda x, then x is an eigenvector and lambda is an eigenvalue, right. So, in a similar way you can see that 2 1 1 2 into 1 minus 1 is 1 into 1 minus 1, right. So, here again you can see that yeah, A x is equal to lambda x with lambda equal to 1 and x is equal to 1 minus 1. So, these were the two eigenvectors of this particular matrix, and when I chose them I actually got the answer. So, can we have a formal proof of this statement? Yes, we can have the proof. I will readily give it now. Okay. So, consider that yeah, you can say V1 V2 dot 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 Vn to be the eigenvectors of H. Okay. So, note that H is a symmetric positive definite matrix, right. So, I mean by basic linear algebra you should have known that yeah, the eigenvectors of a symmetric matrix are orthogonal to each other, right. That means Vi transpose Vj is equal to 0, right. So, yeah, in case you did not know, I mean there is a topic called diagonalization in linear algebra. I mean you can learn that, or you can take it for granted and proceed in the class. Okay. So, yeah, given that H is symmetric, so we have Vi transpose Vj equal to 0 for all I comma j. Okay. And we can also choose them to be orthonormal, that is we can choose them to be orthonormal, that is Vi transpose Vi equal to 1 for all I, yeah, for all I not equal to j I should say. Okay. So, yeah, I can choose them this way. Okay. And you must have also known from linear algebra that orthogonal vectors are linearly independent, right. So, that means I can write x as a unique linear combination of the orthogonal vectors, right. And the way you write them is as follows: x is actually V1 transpose x into V1. So, V1 transpose x is a scalar, okay, plus V2 transpose x into V2 plus dot 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 plus Vn transpose x into Vn. Okay. So, yeah, if they were not orthonormal, I should have also divided by V1 transpose V1 in the first term, V2 transpose V2 in the second term, and so on. But since we have normalized them, I will just use this particular term. Okay. Now, So, yeah, I mean these are some of the basics before I get to prove that yeah, if I so now so with all these as the basics, now consider f of x1 to xn is half x transpose hx, okay, where yeah, so fine, I mean I think I have H is some positive definite symmetric positive definite matrix, and yeah, V1 to V1 V2 dot dot Vn are the eigenvectors of H, okay. So now I will also choose D0 as, okay, maybe I should have wrote it as V naught to Vn minus 1, I mean just to have it consistent, okay, it is okay. So, I will just modify this slightly so that it looks nice. So, I could have also left it as such, but anyway. So, yeah, so I am choosing D0 as V0, D1 as V1 dot 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 Dn minus 1 as Vn minus 1, okay. So, let us see what happens in this case. So, let so yeah, and x0 can be any arbitrary value, okay. So, yeah, let us x0 is just x1 0 dot 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 xn 0, okay. So, what happens if you exactly choose d naught equal to v naught, d1 equal to v1 and so on, okay. So, first note that f of x, which is half x transpose hx, okay, can be written as half so x, if you recall, is what I have written here, okay. So, I will retain this x, but this x I will replace it by v naught transpose x v naught plus yeah, v1 transpose x v1 plus dot 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 vn minus 1 transpose x vn minus 1, okay. Now, what is, so let us write it term by term, v naught transpose x, sorry, h v naught, okay, and h v naught is lambda naught v naught, okay, because yeah, this is an eigenvector, right. Similarly, v1 transpose x into h v1 plus dot 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 plus vn minus 1 transpose x h vn minus 1. So, this becomes half x transpose okay, I will write it step by step, lambda naught v naught plus lambda 1 v 1 lambda n v n, okay. And if I take this inside as well, I will have half into lambda naught v naught transpose x the whole squared plus lambda 1 v 1 transpose x the whole squared plus dot 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 lambda n minus 1, oh it is n minus 1, sorry, lambda n minus 1 v n minus 1 transpose x the whole squared, okay. So, what has happened? We have just modified the axis, okay. Instead of having x1 x2 dot 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 xn, we have modified the axis as v naught transpose x v1 transpose x dot 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 vn minus 1 transpose x, okay. So, if you see in this example where h is equal to 2 1 1 2, the axis that we have chosen are x1 plus x2 and minus x1, sorry, x1 plus x2 and x1 minus x2, okay. So, that is instead of these two as the axis, we have chosen, write it with a different color, these two as the axis. Okay. So, when we turn the axis and do coordinate descent, get the answer. Okay. And what are those axes that we need to choose? It is the axis pertaining to the eigenvectors. Okay. And this is actually very similar to coordinate descent being performed on a different axis. Now, what I have to do is just to redo what we did for the coordinate descent algorithm, right. So, see that at each step. So, we chose an x naught which is arbitrary, and x 1 was just x naught plus alpha naught d naught, where the first component was nullified, right, first component vanished, right. So, we will do the same thing here. So, x 1 is equal to x naught plus alpha naught d naught. So, note that d naught is equal to v naught and alpha naught is g naught transpose v naught by v naught transpose h v naught into v naught. So, note that g naught is actually h x naught, right. So, I will substitute that. So, it becomes x naught transpose h v naught by v naught transpose h v naught, but note that h v naught is actually equal to lambda naught v naught, right. So, this becomes okay, write it here, x naught minus lambda naught x naught transpose v naught by lambda naught v naught transpose v naught, but we have chosen v naught transpose v naught to be 1, right. So, lambda naught cancels. So, you get this is equal to 1, and so x naught is x naught minus x naught transpose v naught into v naught. Okay. So, what does this mean? I have subtracted the projection of x naught onto the v naught axis, okay, like I subtracted the projection of x naught onto the x 1 axis, right. So, that vanished, is not it. In a similar way, here the projection of x naught onto the v naught axis has vanished. Okay. In a similar way, in each step the projection across v 1, the projection across v 2 dot dot dot, the projection across v n minus 1 will vanish, and we will actually get 0 at the end. Okay. So, yeah, I think this is sufficient proof to say that whenever you have a quadratic function in n dimensions, okay, you use this algorithm that the direction that you choose at each of the n steps are just the eigenvectors of the Hessian matrix of the quadratic function, okay, and at the end of n steps you are sure to reach the final answer. So, all right. So, in that case what is the problem? I mean, so have we completed at least the case of quadratic functions? We can say so, if we are ready to find the eigenvectors. Okay. So, the issue is that finding all the eigenvectors of a matrix when n is large is actually computationally expensive. Okay. Even taking the inverse for that matter is computationally expensive. Okay. Otherwise, we could have even done H inverse B, right. So, if you take half x transpose H x plus B transpose x plus C and what you want to minimize it, it is just minus H inverse B, right. So, inversion is expensive and taking eigenvalues is even more expensive. Okay. But nevertheless, if we are ready to bear that expense, this would suffice. Okay. So, I mean, I will teach you about a method I mean which in which you actually need not find the eigenvectors in the next lecture, but in this lecture I will actually tell you how to find the eigenvalues in Python. Okay. So, I mean with that we will complete the lecture. So, I will import NumPy anyway as we usually do, and so suppose I am given some matrix. Okay. So, let us say yeah, so I am doing it for a general matrix. Okay. So, it could be, for example, it could be negative definite or indefinite or anything, it need not be positive definite. Okay. So, I am just doing it for any matrix possible. Okay. So, let me generate a random matrix, say 3 comma 3. So, I mean just to okay, sorry. I suppose this works. Printed H. So, yeah, I need to say from where to where. Okay. So, let us say it is from minus 9 to 9. So, yeah, when I say 10 it is up to 9. Okay. And here I need a 3 cross 3 matrix. So, yeah, this is a new command. It is np.random.randint. Okay. So, what this does is it generates random integers. Okay. So, there are commands like np.random.rand and np.random.randn. Okay. So, they generate real numbers, but np.random.randint generates integers only. Okay. So, what does this command do now? So, when I say np.random.randint comma say L comma or rather S comma L comma some size. Okay. So, I will possibly write down the syntax here, np.random.randint comma S of S comma L plus 1 comma size. Okay. So, what this means is it generates integers starting from S. So, it includes S, but it does not include L plus 1. So, it can be S, S plus 1, S plus 2 dot 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 L. Okay. So, it generates integers in this range. Okay. And you can give the size, you can give a one dimensional size. So, if you just say 100, then it generates 100 values. If you give something like 5 comma 6 or something, it generates a 5 cross 6 matrix and so on. Okay. So, since I want a 3 cross 3 matrix, I have generated like what I want it to be. Okay. And so, one thing is this is not symmetric. So, I will make it symmetric by doing this H plus H transpose by 2. Okay. So, now you can print H again to see what happens. Yeah. So, this was not symmetric, but this has become symmetric, right. So, as simple as that. Now, fine, yeah, all this is fine, but now how do you find the eigenvalues and eigenvectors of a matrix? Very simple, you just write this command. So, I will print that as well, np dot linalg dot eig. Okay. So, that is the command. Okay. So, you can see that the eigenvalues of this matrix whatever you have here 4 minus 4.52 minus 4.51 minus 62 minus 60 is 10.152, 0.675 and minus 5.828, and the eigenvectors are 0.613. Yeah, this is the eigenvector corresponding to 10.15, this is the eigenvector corresponding to 0.675 and this is the eigenvector corresponding to minus 5.828. Okay. So, if you want to access them separately, okay, so you can give the following. So, you can write it as V comma Q. Okay. So, V is the set of eigenvalues and Q is the set of eigenvectors. Okay, I am sorry, there was a bracket that I need to have removed. Yes. So, this is the matrix that we are looking for, and V is the set of eigenvalues and Q is the set of eigenvectors, and they are corresponding to one another. So, this is corresponding to minus 7.6, the second line, second row is corresponding to 1.259 and the third row is corresponding to 4.353. Okay. So, yeah, this is how you find the eigenvalues and eigenvectors. Okay. And so, if you want to I mean do the perform the final algorithm. Okay. So, you can choose this particular code. Yeah, given that we have looked at how to find the eigenvalues and eigenvectors of a given matrix, we will now code the algorithm that we just discussed using Python. Okay. So, we will have the following starting value 1 1 1 and the H matrix, let it be yeah, now it has to be a positive semi definite matrix, sorry, positive definite matrix and symmetric. So, yeah, what I am writing now is I mean has all those characteristics. Okay. So, you can see that it is symmetric, and yeah. So, I will print the yeah, eigenvalues, so that you can verify that it is positive definite. Okay. So, this is np dot linalg dot eig of H. Okay. So, I will just print V, sorry. So, you can see that the eigenvalues are all positive. So, it is I mean the matrix is symmetric and positive definite, fine. So, now we will write down the algorithm. Okay. So, yeah, so we can start with k equal to 0 and while np dot linalg dot norm of so now we have to write it as Hx is greater than 1e minus 6. Okay. So, D is Q of, so it is the kth column. So, since I have put k equal to 0, it is the 0th column that I have, so it is V 0 basically. Okay. And yeah, so maybe I will print this because I want the values anyway. So, with the format specifier it is of this form. So, I am going to print k x of 0, x of 1, x of 2 and yeah np dot linalg dot norm of h into x, and so alpha is minus d dot h at x by d dot h at d, and x is equal to x plus alpha into d, and k plus equal to 1. And finally, I will print this here as well, so that we know the final answer. So, you can see that this was a 3 cross 3 positive definite symmetric matrix, and we got the answer in 3 steps. You get the answer 0 0 0. Okay. So, again you can use this algorithm, you just have to change x and h. X is the initial value and h is the matrix that for which you are finding the minimum, that is when the function is half x transpose h x. Okay. So, you can use this code, and that would give you the solution. So, let us end this lecture. In the next lecture, I will speak about another algorithm where you actually do not need to use the eigenvalues, okay, but you can still come up with the answer in n steps. Thank you.